I was posed a rather interesting question as to external flowing and flow analysis in FreeCAD and the ability to flow across a gradient. The question was, if you have a city, could you simulate wind and have wind near the ground go slow and wind near the top go faster, so it's like an inlet on a gradient? The short answer is, to my knowledge, I don't believe FreeCAD CFD Open Foam is going to support that just using the GUI like my videos do. But I think that there's a way around it if you want to use the GUI and don't want to bust into the more technical aspects that are like programmatic and whatnot. So let's focus on that. So here I've made a small model of a city, 6 buildings. Kind of reminds me of New York or Chicago. Maybe the Ninja Turtles live in here. Let's create another solid. And I've used, of course, part design to make my city. I'm going to just jump into the sketcher and use the part workbench for my other solid. I think I can get a pretty clean subtraction that way. So what I'll do first is jump into my polyline tool and make a bunch of lines, vertical, of course. All right, I'll use the V key to make this one that is off vertical into a vertical, and V here as well. I have this already horizontal, so we're good there. Let's grab our origin and this outer point and say Shift V to add a vertical dimension. Let's say something like 6.35, I think, and that puts the line right at ground level. Let's highlight all of these lines, and I'm going to say E for equal. And it looks like I do have to select just the lines and not box select them. So let's select every line. E for equal. Let's select this over here. Shift V, let's say 0.25 meters. Shift H on this line, and we'll give this, say, 0.5 meters. Now, I made this short for meshing computation reasons, right? If you're doing a serious analysis, of course, you want to take the distance of the flowing part that you're using and go about 10 times that distance for a good analysis. But this is for demonstration purposes only, and I'm going to be running that abbreviated. So you can tell we're not constrained here. Let's grab this endpoint, the plane in between, and hit the S key to make it symmetric. We'll close and add from the part workbench an extrude on this sketch. We'll go isometric. We want to go with symmetric to plane, and let's say 250 millimeters. Great, so now we have an extrude and our city fitting in it. You can tell this is not scaled to the size of actual buildings. I know SolidWorks only has like a mile or maybe up to a few miles envelope of build area. That doesn't give you the size of a city. I don't know what FreeCAD's limitations are, but I think scaling things down is very beneficial. If you need to be super precise, you need to use Reynolds number to be able to scale things down. So let's add a cut, right? I'm going to highlight my extrude. I'm going to hold control and highlight my body, and we'll do a little cut here. And as you can tell, we've cut out our body that makes it able to flow. Great. Looks like I'm having a bit of a graphical anomaly. We'll see if that affects our analysis moving forward. Next, now that we have our cut, we can go to the CFD Open Foam workbench and create an analysis container. I want to make sure our physics model is viscous with laminar flow Fluid properties look good with air. Our initialized fields, I'll change that to potential flow, or even we can specify values and leave them at 0. And then we have our solver. Let's stand on this body and create a mesh. Let's say that we want our mesh to be something like 5 millimeters. And we're using CF mesh, so we're going to write our mesh case and run the mesher. All right, so it looks like our meshing is completed. We'll load the surface mesh and take a look. Yeah, that looks like a tight enough mesh for what I'm doing with all of this. And I like the way that that turned out. So we'll close that. And we'll go to our mesh and hide it with the space bar. Next, we need to set up boundary conditions. And yeah, I think all of our faces are highlighting pretty well. So I think our graphics anomaly is just an anomaly, I'm hoping. Let's grab our first thing. We're going to say an inlet, and let's say that this is 1 meter per second at 100 kilopascals or 10,000 pascals. We're going to say OK to that. We're going to highlight this next one. Oops, and I created an analysis container. I'm going to hit Control-Z on that and set up another boundary condition. Another inlet. This is going to be 2 meters per second and 100 kilopascals. And we're just going to keep on going. Now you can argue that setting this up in kind of hard lines isn't very accurate. And I mean, to an extent, yeah, you're right. So is meshing and things like that. So I kind of roll my eyes when people have this idea that, you know, there's a right way to do things and then there's no other way to do things, because that's not how this works. And I get comments like that sometimes. I mean, the saying goes, all models are wrong, some models are useful. And I think that's absolutely true, because that's why we use tolerances in engineering, right? If we can mesh something tightly, we can run this face thing tightly, and it's all an approximated model. It's the same principle as meshing. So it's more a question of, is this going to be useful to you in your particular need? Because various situations call for various levels of precision. So I don't really like the all or nothing approach that some people have in their mentalities. Let's go with this one. The other thing is, of course, we're scaling our city, and we may need to not only account for Reynolds number, which I'm not really doing here, and I'm not really giving too much of a care of how much pressure I'm dealing with. I think this needs to be 5 actually. 1, 2, 4, yeah. But also we may need to do some fancy thermodynamics and make sure that if it matters to us, we would drop the pressure as the fluid accelerates, because you would see pressure changes in a moving fluid. So it depends on just what kind of resolution you need, you know. And if you're going to do flow analysis, you really need to have thermodynamics knowledge if you're going to go, you know, super technical with it. So we're going to take this inlet. I think we're already on 7. And again, 100 kilopascals. All right, so I think I'm going to end my rant there. I think we covered everything. Let's go with 8. And of course, we're doing this in the Y direction and the positive Y direction, right? Not the negative Y direction. But I've already talked about that in a different video. Great. Okay. Inlet and 9. One, 2, 3, 4, 5, 6, 7, 8. I guess that should be 8. Is this one 7? That one should be 7. This one should be 6. Am I just one off or am I counting wrong? 1, 2, 3, 4, 5, 6. Yep. So this one should be 5. Yep. Okay, so I missed a number at one point. This one should be 8. We'll add another boundary condition. This is our 9. Inlet. That's what happens when you talk and model. All right. Inlet. 10. Too many. All right, so we got our pressures worked out. Let's select all of our faces. I'm holding the control key to select, of course, and add a boundary condition. We want a wall, but a slip wall. And then we're going to take this last face and create an outlet. Leave everything at 0 for the outlet. All right, so we should have good flow flowing across our little city. I don't normally like it, but in this case, if you have to flow at an angle, it might be worth it just to take one solid and turn it with the transform, right? Like I can take this body and select that transform and turn the city to flow at an angle. It might be more simple than trying to establish, the angle of a flow elsewhere. So we've got the city and we have our boundary conditions. We're meshed. Let's save this. Let's open up our solver. We'll simply write and run our case. I'm not expecting great results because I didn't spend a lot of time on that city. I just needed something to demonstrate, so I'm not expecting to go to 10 to the -4th or anything. In fact, I've just finished a simulation successfully, which isn't a very good sign. We'll run to pair view and see what happened. So in pair view, I come from the bottom. It looks like there is no flow whatsoever. We can add a stream tracer and hide and show the stream tracer, and yep, absolutely nothing. Let's run back to initialize fields, potential flow, and rerun our solver. Again, based on how I've modeled and everything, I'm really not expecting too amazing of a solution. Looks like we had a floating point error now. So again, change your potential flow to potential flow, right? Initialize fields into potential flow, I mean. And let's change this to Gmesh. That's tetrahedral. We'll write the mesh case and run the mesher. Again, I think I'm not being thorough enough on my potential flow if I specify zeros. So I'll just change it real quick back to potential flow, and then Gmesh probably will clear out our floating point exception error. All right, so it looks like our meshing completed here. We'll load the surface mesh. Great. Yep, tetrahedral, looking pretty good. So we'll clear the mesh, close, run to our solver, write and run our case. Alright, so we're partway through, and you can analyze and view stuff as the analysis is running, which is pretty cool. As you can tell, these residuals are horrible, So we're not expecting any degree of accuracy, which is okay because I know I didn't spend a huge amount of time getting this set up. But I can click on the Pair View button, which will bring up our Pair View viewer. And looks like we don't actually have results yet. So let's let this go for just a bit longer. All right, now it looks like we've got some results, so let's take a look here. And yeah, I'm kind of excited to see what it looks like. It looks like we already have some visual results in this area. We'll grab Stream Tracer, and we'll turn on Stream Tracer and turn off our results. Again, the colors are pretty. Do not trust these results because the analysis really didn't run that well. Looks like we don't have that good of a stream tracer, right? We shouldn't expect flow like that. But let's change this to a point cloud and see what's going on. Again, this is likely due to our very poor residuals. We'll change this to something like 1,000. All right. It's kind of erratic. You can see where the air is flowing around the buildings that we have. I want to up this maybe by a factor of 10. Yeah, there you go. Let's change this to U. Wow. Make this 5,000. Well, it looks like I have to move my point cloud to the right spot. Okay, there we go. We can also try to scale this with vorticity. And I can add a little bit more color to my stream tracer. Yeah, we're just getting a very extreme point right in here that seems to take up all of our visual color scale. So that's pretty interesting. Again, these are very poor results, but you could tell that that is a way to do more of a gradient input. Again, I think the poor results are partially due to the fact that I did not model my city very well. I probably have some sharp edges or the need for mesh refinement or any number of things that could go to having bad results. But again, the idea is if we just subdivide some faces and change their velocity, and depending on how many faces you use and depending on what kind of pressure gradients you need, that could be a way that works pretty well. All right, so I'm here flowing another version, right? I just, same city, just, different number of inlets and different increment of speed between the inlets. You can download this one from GradCAD 2, I think. And, just different flow envelope. The residuals are still not good, but better than last time. And if I run into my solver, and load my results into Pair View, these are the results, right? They're looking a lot more interesting so far, and I think that little scaling issue that we ran into is a little bit better. Let's open our stream tracer and make that visual, right? So you can see how we flow off of one flat plane from the line, which the line is really interesting, but I'm a fan of the point cloud at the end of the day. So let's apply that point cloud. Right, you can start to see we're looking at pressure here. So how the pressure changes, you get a pressure drop in between the buildings, which is what you would expect, and it looks like a good deal of turbulence in between the buildings. Also, I think that's kind of understandable and what you would expect. If we look at velocity, you can tell exactly where the velocity changes as you would expect. So I think these are probably better results. Again, you can download some GrabCAD if you're interested. We can look at vorticity and see, of course, areas of greater vorticity are where you'd have more rough flow between the buildings. So I think this is actually not something that you would trust due to how our residuals look, but at least a little bit more interesting. So hopefully this is kind of a fun way to explore gradient in inlets, and hope this was helpful. If it was, please subscribe, and I'll see you in the next one.